Good morning. Today's subject is the shear stress development in the beam problems. So far we discussed how to calculate the normal stress development in beam problems, right? We discussed how to calculate the internal moment from the definition of deformation using the curvature. So once we have internal moment, then using the assumption of the linear distribution of the normal stress over the cross section of the beam elements, then we were able to calculate the distribution of normal stress. That's what we discussed up to the last time. Today we want to talk about the development of shear stress. Okay, the discussion of shear stress is rather long story. That's why I wanted to discuss this subject in the new, this new lecture. Okay. Before we talk about the shear stress, the formula for the shear stress, let's try to have overall figure intuitively. It is always understanding, it is always important to understand the problem intuitively. Okay. So let's consider a cantilever beam made from a cardboard papers. Okay. For example, okay, wait a second, please. So instead of paperboard, you may imagine a book here. So I have a textbook here. So you can imagine that you bring a textbook on your hand, and then you try to apply a force here. So if you apply force here, then without gripping the book, together, all the pages, then what happens is you have kind of large deflection here. That's what happened is shown in the first figure here. So here in the first figure, each pages are slided against each other. Okay, so each page slides against each other. So we have certain kind of the shear deformation between the layers. Okay, but what happens? So if you grip the end of the textbook, then all the layers would deform all together. Okay, in that case, the stiffness of this the book becomes much higher than before, isn't it? So I'm talking about this situation. So in the second situation, if the balls, all the layers are bonded together, then the stiffness of these cardboard beams becomes much higher than the first case. Okay, so here. This is a summary. A section layered with multiple cardboard would undergo deformation with the shear displacement between layers. Okay, that's what I told you. But if you consider the structural beam elements, there is no such the interlayer displacement. Okay, there is no such situation. So which means it is very natural to imagine that there is a certain kind of bond mechanism between the layers, isn't it? So for example, let's imagine that we have a rectangular cross section here. Then if you apply a load to the end of the beam, which means if you imagine some multiple layers forming these cross sections, there should be some glue action between layers, is it right? So we have some bond action. So let's talk about this bond action today. You understand? Okay. So now let's try to consider the real problem here. So I want to consider a beam subjected to a distributed load. If the load is distributed with some constant traction, then now at this moment you know how to construct the shear force diagram and bending moment diagram. So if you construct the shear force diagram here, as shown in here, shear force diagram, because this is linearly distributed. So do you remember? So the change of the derivative of shear force over the coordinate is equal to minus of the q. So which means the shear force, the derivative, the slope of the shear force diagram is constant with the minus sign. So which means my shear stress starts from the maximum value, and then linearly decreases, isn't it? That's the shear force diagram that we can imagine here. So now we want to consider a small segment here. Small segment, the whose its width is measured by dx, okay, dx. So let's exaggerate, let's zoom in the cross section here. So if you look at the situation here, in the left hand side okay, so for example, let's say this is my coordinate x, and then this is the position x, okay, the reference position. The reference position, there must be a reference bending moment, the reference the shear force, isn't it? So if we move my point by dx, then there must be change in the bending moment dm, and the change of shear force dv, isn't it, right? We must have some certain changes. And then further, we want to focus the force equilibrium on another small segment as shown in here. Back. Okay. Yeah. Another small segment. So yes, I want to talk about the free body diagram here. And then because of this bending moment, I must have some stress field, so acting on the left-hand side of this small segment. On the right-hand side also, I have stress field. And this stress field is a consequence of this bending moment, which means if I want to say that this stress field is given by sigma, and the right-hand side, my stress field should be, sigma, but there must be certain change, the sigma, isn't it? Yeah. So we want to talk about this problem. So let's check. Instead of dealing with the stress field directly, because the stress changes linearly, that's why it is better to integrate the normal stress over this cross section. So we have internal force here. So let's try to calculate the internal force. The internal force is integration of normal stress over the cross section. Then here, because of flexor formula, now we can replace the normal stress sigma by the bending moment, and then y position, and then second moment of inertia. So make sure here I drop the minus sign, because we consider the equilibrium for this small segment. So if you understand, so we want to compare the change of the forces on the left hand and right hand side, and we don't have to worry about the minus sign here, because I want to check only the changes. And then, as I told you several times by the logic here, the moment is the reference parameter, or with respect to cross section. In cross section, we have only one bending moment. That's why we can take out the bending moment into the front of the integration. And the second moment of inertia is also the representative value. That's why we can take out. Okay, that's why we have bending moment and the second moment of inertia here. And then we need to integrate. We need to calculate this integrate over this small area. This is delta A. And then by the definition, so because nobody likes such kind of integration, I will replace this integration by using a variable q. The variable q is called first moment. The first moment of this small cross section with respect to neutral axis. Okay, this is the quantity of the q. Then we have, this is the definition of T. The internal force acting on this small segment can be calculated by the bending moment, and then first moment divided by second moment of inertia. Okay, this is what I did for the left hand side. So let's look at what happened in the right hand side. In the right hand side, my stress increases by the delta sigma. The delta sigma means delta sigma is caused by here the change of bending moment. That's why my change of internal force must be given by the change of bending moment, not the change of first moment and the second moment of inertia, because we are talking about a beam section with constant cross section, isn't it, right? So now let's look at the force equilibrium for this small body here. Then on the left hand side, I have T, the internal force T, left hand side. And the right hand side, I have internal force T plus change of internal force T. And then if you look at this, then it is cancelled, isn't it? So I have non-zero dt. The force equilibrium cannot be satisfied. Okay, let me explain what happened here on a new page. So small segment by the integration. So we have t here, and then we must have, because there should be little change, dt, isn't it? This length is dx. Okay, and then make sure that here t and dt is the consequence of the normal stress, isn't it? Okay, normal stress. And then if you imagine a beam problem, there should be the shear stress too, isn't it, right? The shear stress. So we must have the shear stress. Okay, and then because this is a reference point, I need to have shear stress T, and then my shear stress also changed by T tau plus not T, sorry, the T tau, isn't it? So according to the definition that we made last time, is we introduced a new parameter, a new variable called shear flow. The shear flow was what? The shear flow was the shear stress times the thickness, isn't it? So the reason that I want to talk about shear flow is, anyway, to check the force equilibrium, so we need to integrate the shear stress over the cross section. So instead of dealing with the shear stress, so anyway, because to calculate the shear force, the overall force, overall force by the shear force is what? Shear stress times the thickness times the length, isn't it, right? That's what we have to do, okay? But that's why instead of talking about shear stress, I want to talk about these two in terms of the shear flow. That's what I want to talk about. The problem is the shear stress is not constant. Here also we have shear stress tau, and then on the right hand side, shear stress must changes by d tau. So which means the force becomes what? Tau plus, and then okay, it becomes a trapezoidal, and then tau plus d tau, and then we need to multiply the area, isn't it, right? Thickness times the length dx, and then because this is trapezoid and we need to multiply it a half, then what happened? I have a small quantity d tau and dx, that's why it is dropped, it is negligible, and then I have factor 2, that's why we can drop a tau. So finally I have what? I have tau times t, it becomes shear flow, and then shear flow times dx. This is what happened. Okay, so that's why on the right hand side I have shear flow times dx. Okay, the procedure behind this equation is explained in this note. Take a look at it. And then if you move dx to the left hand side, and the change the shear flow per unit distance can be given by the derivative of the internal force acting on the small segment with respect to dx. So let's plug this quantity into here. Then finally we have this dm times the first moment, and then dx and v. What is this? dm over dx is the shear force, isn't it? So finally we can obtain for beam problem, the shear flow can be obtained by shear flow on certain point in beam cross section. For example, let's consider an I-shaped section for beam problem. Then at first we have to calculate, at this point we need to calculate the bending moment and the shear force, okay? And then let's say I want to calculate the shear stress or shear flow at this point. Then what we have to do is we need to calculate the first moment for the cross section. This is the Q, and then we need to calculate second moment of inertia over the overall section. This is the second moment of inertia of overall section. Okay, and then plug in the shear force V. Then I can calculate shear flow at this point. So if you are interested in the shear stress instead of shear flow, then what do? Then we divide shear flow by the thickness. Then we can obtain the shear stress tau. You understand? Okay, so now let's try to discuss the calculation of shear flow in general section. I already gave you the brief overview for the calculation of shear flow for I-shaped section. So now let's imagine that I have a beam with a cross section of I-shaped cross section, and then in our calculation, when we calculate the bending moment or reactions and whatever, so we idealize overall section with a line is in. Okay, with a line here. So with this line, so we calculate the bending moment, and then the change of bending moment. Also we calculate the shear force here, and then change of shear force. Okay, we drew the shear force diagram and then bending moment diagram. And then we want to calculate the shear stress at this point. Okay, shear stress at this point. Then shear stress is shear flow divided by the thickness. So I'm talking about this thickness. Okay, the thickness in this direction. Okay. Then the procedure is given here. The first we have to calculate the force acting on this small segment. Okay, small segment, and then the shear flow is given by the shear force on this cross section, shear flow on this cross section V, and then we need to calculate the first moment for this small segment Q, and then we divide this quantity by the second moment of inertia. That's how we can calculate the shear stress at arbitrary point. Okay, then let's try to understand the flow of the direction of the shear flow. So if you calculate, if you imagine a case with the positive bending moment, so we must have compressive stress. Let's say we have bending moment, and then the bending moment increases, for example. Then we, because I have more compressive force on the right hand side, then which means my shear stress is what? My shear flow, to satisfy the force equilibrium, I need to have shear flow in this direction. And then because of the principle of angular momentum conservation, the direction of shear flow in the cross section in this direction. So we have same logic on the left hand side of my cross section. Then this is the direction of shear flow. So the shear flow converges to this point. And then if you calculate the shear flow further for this web, and then shear flow goes down. And then here I have an error in my lecture note. And then on the bottom flange, the shear flow must go out. The diverges to the side. Okay, this is the direction of shear flow. And then how about the channel section? In the case of channel section, my shear flow goes in here and goes down. On the bottom flange goes to right. Okay, depending on the loading condition. So now let's talk about another issue. Actually, we're gonna talk about this issue later when we talk about the shear center. So when we talk about the shear center, we will revisit this issue. But make sure that how we calculate the shear flow. So when we calculate the shear flow, we we just, the formula for the calculation of shear flow is shear force. We consider, the point where we calculate the shear flow. So we consider first moment, and then we need the information of the overall section, the represented by the second moment of inertia, and then we multiply the shear force. Okay, we multiply shear force. Okay, let's imagine a beam section. Here we have I-shaped section and the channel section. And then let's try to apply the load on the top of the beam section. So if you apply the load here, then we can calculate some bending moment and shear force, isn't it? And then what if you apply load here and here? Is there any difference? So what do you think? So here I gave you three different positions where we want to apply the loads to these beam problems. Do we have any difference in the magnitude of shear force and bending moment? So make sure that beam problems are two-dimensional problems, okay? In two dimensions, so there is no way to distinguish the position of the loading point in the cross section. So in beam problem, wherever we apply the load, the shear force and the bending moment is same, okay? But obviously, so if you apply load here, then that's gonna develop non-zero torsional moment, isn't it? And also this guy causes non-zero torsional moment. So for this load, so if you choose, the reference point here, because the shear flow is symmetric, and the torsional moment produced by the shear flow over the cross section is equal to 0, and then the torsional moment caused by the external load is also equal to 0. So in that case, the force equilibrium in the sense of torsional moment is satisfied. But problem is, if load is applied here, so if load is applied here, and then the torsional moment caused by this loading is not equal to 0, but the torsional moment caused by the shear flow is equal to 0. So which means, the force equilibrium is not satisfied. So not to produce any non-equilibrium torsional moment, we need to apply the load here, exactly at this point. Okay, this point is called the shear center. And in the case of channel section, okay, look. So as I told you, we must have this shear flow here, like this. The shear flow is like a turnaround. So it introduced some kinds of non-zero torsional moment. So if you consider a reference point here, and then to prevent the non-zero, or to satisfy the equilibrium of this non-zero torsional moment caused by the shear flow, so we need to apply the load not here, okay? So if you apply load here, and the torsional moment produced by the external load is equal to 0. That's why we cannot satisfy the force equilibrium caused by the shear flow. And then rather than that, we need to apply the load, somewhere here. So that produce, the torsional moment in the opposite direction, not to cause any non-equilibrium torsional moment in the cross section. This is called the shear center, the place where we need to apply the load to satisfy the two-dimensional the problem definition of the beam problem. Okay, so please keep in mind that the concept of shear flow, concept of shear center, the shear center concept of shear center comes from that. So we developed all these beam theories in two-dimensional problems. It is a defect of theory itself. Okay, we never discussed where we apply the load on the cross section. Okay. And then here we have a shear formula. So as I told you, once we calculate the shear flow value, and the shear stress can be obtained very easily by dividing the shear flow by the thickness. Okay. And then now let's consider an example. Shear stress in a rectangular cross section. For example, let's do an example here. Okay. The shear flow, calculation of shear flow is given by the first moment divided by second moment of inertia, and then it should be multiplied by the shear force. Okay, so once we are able to construct the shear force diagram, and that comes from the shear force diagram automatically, and then that comes from the the overall cross section, the second moment of inertia. So no problem. So we can calculate anytime. The problem is Q, isn't it, right? So in this example, let's consider a rectangular section. In this problem, we want to consider this is the width is B, and then the height is H. Okay, is it correct? Height is H, yes. And then we need to find the neutral axis. In the case of rectangular section, the neutral axis, we already know the position of neutral axis. So neutral axis is here, y coordinate. And then the height is equal to h over 2. So now we want to calculate the first moment, the shear flow in position measured by y. Okay, let's say, so we want to calculate the shear flow acting on this cross section here. So which means we need to calculate the first moment for this. So let's try to calculate the first moment. So first moment Q is defined as what? The y coordinate dA. So what we have to calculate this integration for this small rectangle. Again, so we can use the mean value theorem. The mean value theorem is we take out the geometrical centroid and then we consider the just cross-section area of this hatched area. Now first, let's try to calculate the hatched area. And this is equal to, first we need to consider the width, B, and what is the height? Height is what? H over 2 minus y value, isn't it? This is the area. And how about the distance to the geometrical centroid? Distance to geometrical centroid is what? H over 2 minus the half of the thickness, isn't it, right? Minus half of the thickness, sorry, there's no space. So half of the thickness. The thickness is given by h over 2 minus y. This is the thickness of this. So if you rearrange this is h over 2 and the minus h over 4, and then the minus a plus y over 2. So that becomes what? That becomes h over 4 plus y over 2. And that becomes is a half h over 2 plus y. Okay? Then my first moment becomes what? The Q is a half of h over 2 plus the y coordinate, and then so here, because we have b and the h over 2 minus y, and using the high school mathematics, so we have h square over 4 minus y square. This is the first moment. Okay, let's check my calculation. So I have h square and divided by 4 and the y square, and I have factor 2. And then make sure that we have shear force and the second moment of inertia, isn't it? So according to this equation, so if you plot the change of shear stress over the y-axis, for example, so y-axis, then my shear stress is equal to 0, so equal to 0. So on top, isn't it? My shear stress is equal to 0 on top. This is so y-axis and my shear stress, and then my shear stress is equal to 0 on top here. This is the point of h over 2 is equal to 0. And then my shear stress is changes quadratically, isn't it? Changes quadratically, and it becomes maximum at the center. So maximum shear stress is given by this equation. Oh, by the way, I forgot the width, thickness, width, sorry. So B is cancelled, okay? B is cancelled. That's why I have maximum shear stress. So maximum shear stress is around 1.5, and then average shear stress, okay? 1.5 times the average shear stress. Let's consider circular section. So we can handle a circular section similar to rectangular section. So what you have to do, if you want to calculate the maximum shear stress here, then we calculate the first moment for this half circular area. A problem in the case of the circular section, we have the shear stress in the vertical direction only here. But in the case of here, for example, let's say you want to calculate the shear stress over this cross section, because I have traction, surface traction is equal to 0. So which means shear stress acting on this section is not in the vertical direction, okay? Rather than that, it is inclined. That's why this formula, VQ and IB, cannot be applied to this cross section. So in the case of circular section, this formula can be applied only here, okay? Only here. This is a limitation. And how about I-shaped section? In the case of I-shaped section, we calculate the first moment. For example, if I want to calculate the shear stress at this point, and then we need to calculate the first moment for this. It's Q. Okay. Actually, the calculation is quite complicated. That's why I don't want to follow this calculation procedure in this class. But maybe you want to try in your place. So if I give you a tip for the calculation of the first moment, this is the tip. Okay, say we want to calculate the this is y, and then we are calculating the first moment for this. The definition of first moment is Q times Q is equal to y and dA. So we still use the mean value theorem, the area of the section. And then first, this is very similar to this. And then we want to consider large section, y bar for the large section, the area for the large section. And then we subtract, okay? We subtract small section, negative section, what I mean. We subtract this negative section. So minus y bar to the negative section, the area to the negative section. So in the case of this large section, positive section is up to here, isn't it, right? This is the distance to the geometrical centroid. Now how about this negative section? This is distance to the centroid of the negative section. That's how you calculate the first moment of I-shaped section. Although you need to calculate many terms, but the calculation is straightforward. Try to follow the derivation in your place. Okay, so next issue is built up cross section. Here I'd like to take 10 minutes break.